So here's an example that I wanted to work with you. So again, I'm picking really simple sets, just 1, 2, 3, ABC, and I've got two topologies, F and R. And if you just look at these topologies, look at F and look at R and compare them. I missed a squiggle on R, so that's a problem. Now you can compare them. They really look the same in some sense. Different elements, but somehow at a glance you can tell if homeomorphism means at all what we think it means, then these spaces ought to be homeomorphic. So I wanted to look at a function h, and we're going to send 1 to B and 2 to A, and let's send 3 to C. And so the question I want us to ask is H a homeomorphism? And well, first off, let's please note it is immediately clear that H is a bijection. It's 1-to-1 and onto. So let's write that down. It is clear that H is 1-to-1 and onto. And so now we need to think about the preimages. So we need to think about the preimage of, let's start with H. I have to check that H is continuous and then H inverse. So let's start with H. So I'm going to pick, right, H is going from X to Y, so I'm going to pick open sets in R, and I'm going to look at where they look at their preimages. So let's, for example, I'm going to jump right over to C. Let's look at the preimage of the set C. Now, we have a bit of a notational disaster. This is not H inverse of C. This is the preimage. The way that I'm thinking of it is the preimage of the set C under H itself. We'll talk more about when the preimage and the inverse are the same in a minute. But okay, let's think about it. So this is all the stuff in X that H sends to the set C. And so you can see, well, that's just the set 3. This preimage is the set 3. And 3 is not in F. So at that point, we know that H is not a homeomorphism. So H, we can actually say, is not continuous. Whoops, I pressed a button I didn't mean to press. H is not continuous, thus not a homeomorphism. Now, the point of this first part of this example is that here, again, these spaces, they really ought to be homeomorphic. In fact, they are. But that doesn't mean you can just go pick any old bijection that you want, and that's going to give you a homeomorphism, right? The continuity part matters very much. Here you have a bijection that isn't itself continuous. So let's look at another map. Let's look at another function. So let's see if we can squeeze this in. I'm going to move this out of the way a little bit so we have a little more space. So we'll put it right there, erase that arrow, and then we'll put it there. Okay, so now for part B, I want us to consider the function k going from x to y, and we're going to say that k of, let's say, k of 1 is A, k of 2 is C, and k of 3 is B. All right, and so I'm going to again claim that k is clearly 1-to-1 and onto. I'm actually not going to check all the preimages, but I would like you to check that the preimage of all open sets under K remains open, and then you can please look at the preimage of all the open sets under the open sets of X. Think about it. K inverse goes from Y to X. So to show that K inverse is continuous, I pick an open set in X and I look at its inverse under K inverse, its preimage under K inverse, excuse me. So I would like you to pause the video and work those out, and you'll check that this is indeed a homeomorphism. So we can say that K is a homeomorphism. All right, so that's that example. Let me see if I wanted to do anything else in this video. let me make one more comment. And so the comment that I wanted to make was this. If you look at this example, notice how there's this beautiful lineup of the sets, the open sets here, X and F. I can just line them all up. And so in general, what I want you to realize in general is that if you have a homeomorphism between two topological spaces, so here's my space, my set X and my set Y. I know those sets are actually, the sets X and Y have the same cardinality. There's a bijection between them, and that bijection actually carries down to the sets F and R. And so there's a bijection between the sets in F and the sets in R. The number of sets here and the number of sets here are the same. It's not always true that you can say, okay, F has a open set of size, 2, maybe this is in F, and so I'm guaranteed there's some other open set of size 2 over here. The cardinality of the sets in F and Y might be different, but F itself, this set, the set of sets, has the same cardinality as the set of sets R. So let's end this video here. I'm going to give you a definition and then just a couple of comments, and I'll let you guys tackle a few homework problems. And like I said, we're getting close to the end of the course. So